This is a video about my gas boiler. Here it is. It's a Worcester Bosch Green Star RI 15 kilowatt heat only boiler. You can see it only has two controls. This dial turns it on and off, and this dial here controls the flow temperature, so the temperature of the water that's leaving the boiler to go to the radiators and to the hot water cylinder upstairs. I thought it was a good time to make it because its days are now firmly numbered. In a few weeks it's going to be removed and replaced with an air source heat pump. Why are we replacing it with an air source heat pump? Well, that's because this pipe, the flue, somewhere between 1 and 2 tons of CO2 come out of that pipe every year. Just crazy. Now, there has been quite a high-profile campaign for the past couple of years to encourage people to turn down the flow temperature on their boilers. Most boilers, when they're installed, the installer cranks the flow temperature right up to maybe 70 or 80 degrees, which reduces the number of complaints they get about people being cold, but makes the boiler incredibly inefficient. It's the equivalent of driving everywhere at 100 miles an hour and then skidding on the brakes. You might get there a bit faster, but you'll use a lot more fuel to make the journey. So the idea is, by turning the flow temperature down, you make the boiler much more efficient. You encourage it to do its condensing thing where it wastes a lot less fuel, and you end up using less gas to heat your home and therefore emitting less CO2, as well as saving some money. Now, the idea about turning down the flow temperature only really works with combi boilers. Combi boilers tend to have two different temperature controls. They have one for the hot water that goes directly from the boiler out of the taps, and they have another one for the temperature of the water that runs around the house through the radiators. The problem with a heat-only boiler is that it tends to only have one temperature control. So that means if I turn the flow temperature right down to, say, 45 degrees to a sensible, reasonable comfort level for the radiators we have in the house, that means that when the hot water run happens, which is usually in the early hours of the morning, I would have to come downstairs, crank the flow temperature back up to heat the hot water to, say, 60 degrees, and then crank it back down again afterwards, which obviously isn't possible. The other thing that would be nice is to add some element of weather compensation. So with a heat pump or a modern highly efficient gas boiler, you can have a temperature sensor outside, and if the temperature outside is colder, that means the heat loss from your house will be higher, which means that the flow temperature of the water going around the radiators would need to be higher. On the other hand, if it's a bit warmer outside, let's say it's 10 degrees, the heat loss from your house will be much lower, so you can afford to run the radiators at a much, much lower temperature, maybe 30, 35, 40 degrees, to kind of balance out that heat loss and, again, make everything more efficient, reduce the amount of gas that you use. Now, gas boilers such as this one, their modulation isn't great. So even if you drop that flow temperature down as low as you can, you're still going to get some cycling where the boiler just kind of heats up too much and then turns off and then lets it drop and so on. But any element of weather compensation that you can add should help a little bit. Because I'm a bit of a geek and I enjoy making things, I had a go at solving this, and again, I thought it would be good to share this and get it out in the world before the boiler gets ripped out and replaced with a heat pump, which does all of this stuff itself. So here's the solution that I came up with. As you can see, it's two pieces of foam kind of construction board. On the front are 4 magnets mounted onto bolts, which have got nuts on that kind of hold the two pieces of foam together. If I flip it over, this is a Raspberry Pi Pico W, which is a very cheap microcontroller that has input-output pins and a Wi-Fi connection. This is a special servo controller board which sits underneath the Raspberry Pi and allows it to interface with servos. This is a servo, so this is a little motor which you would normally find in something like a radio control car to control the steering. And attached to the bottom of the servo is this rubber grommet, which is kind of tapered and is glued on to the end of the servo. This whole thing is attached magnetically to the front of my boiler over the flow temperature dial, like that. And that little noise was the servo controlling the temperature knob and calibrating it to the level that we want it to be at. And I'll explain how that works now. So outside here, in this alleyway down the side of my house, is a little temperature sensor. It's an Eve Outdoor. You can see it 16.7 degrees at the moment, and that's connected to HomeKit, so that sends the temperature readings back into my my HomeKit system. This is the web app that I wrote to kind of visualize and control all of this stuff. So you'll see at the top, this is temperature sensors around my house. The blue line at the bottom is the outside temperature. I've chosen a day when it was a bit colder, back at the end of February. So you can see it's kind of dips down to 2 or 3 degrees and then climbs up to maybe 6 or 7 or 8 throughout the day. This is my data. This is data coming from my my Hive heating system. So the orange bands across the graph are when the heating is on. So the boiler is creating heat. The red line is the actual temperature as measured by the Hive thermostat. And then the grey dashed line is the target temperature. So that's the temperature that I've said I want the house to be at. So you'll see that we have a setback temperature overnight of 19.5 degrees, and during the day we have 20.5 degrees. Now this is the really interesting graph. So this shows the flow temperature of the boiler, and this is done by having a couple of little temperature sensors which are clipped to the flow and return pipes going in and out of the boiler. The red line is the flow temperature, the blue line is the return temperature, so that's the temperature of the water when it comes back, having been round all of my radiators. And here the dashed grey line is the target temperature. So this is based on a calculation from the temperature that is measured outside using the sensor that I showed you earlier. And that is run through a simple formula that computes what temperature the radiators should be at in the house for that outside temperature. So you can see it slightly varies through the day as the temperature outside changes. It's also worth having a look at the vertical kind of orange line, a yellow line that's kind of just before the 6 a.m. marker on the graph. That is the hot water run. So when the hot water run happens, i.e. the boiler is used to heat up the water in my hot water cylinder, then we have a kind of programmed override temperature where the flow temperature changes from the weather compensated controlled level of about 50 degrees here, and it jumps up to 60 degrees. And you can see here at the very bottom chart, if you ignore the kind of changes on the right hand side, on the left hand side you can see corresponding with that hot water run, the top and bottom temperature of the water cylinder jumps up accordingly. Now this is a little bit more complex to read because I also use my eddy with the immersion heater to heat the water cylinder, but really what you want to look at here is the orange line, which is the temperature of the bottom of the cylinder. When that hot water run happens, the temperature of the bottom of the cylinder jumps up from somewhere around 30 degrees up to kind of 45-50 degrees, which is the temperature that I normally have the hot water cylinder at most days. Now the next thing to show you is if I go back to a Sunday, so look at the same graph, you'll see here the water get the bottom, that orange line, the bottom temperature goes much higher. It goes all the way up to 60 degrees. And correspondingly, you'll see that the flow temperature override on this graph is again much higher. It's 75 degrees. What that is that once a week I run a Legionella cycle. So that means that I heat the temperature in the water cylinder all the way up to 60 degrees in order to kill any nasty bugs and bacteria that might be living in there. Now I should say that all the code that I've written for this, so that's both the code that runs on the microcontroller, the Raspberry Pi on the device, and also the code for the web app that I just showed you, is completely bespoke and specific to my house and doesn't really generalize very well. So I would say that you're not going to get an off-the-shelf solution here. If you want to take on a project like this, and I would encourage you to do so, make sure that you're really confident both with the electronics side of it, so actually assembling the hardware, but the software side of it too. You know, you need to be able to write that code that will control the servo, will read the temperature, and will decide the temperature, the weather compensation curve, and all of that kind of thing. I'm happy to answer any questions in the comments, but I'm not going to be, unfortunately, providing the code for my own home control system because it is very bespoke to me. So does this actually make any difference? That's a very difficult question to answer, but just to give you an example, I've gone back to the 23rd of February this year. Now, what happened on this day is that something went wrong with the device. I think it dropped off the Wi-Fi network, so I had to pull it off the boiler. And I just set the flow temperature to a fixed value. So you can see here on the red lines, they're all just peaking at probably somewhere around 55 degrees throughout the day with no weather compensation control at all. And you can see that the outside temperature here, so the blue line, varied between kind of 5 degrees overnight up to maybe 7 degrees during the day. So let's say an average temperature of say 6 degrees. Now the next day, the 24th, the temperature is actually, there's a lot more variation in it. So it drops down to 0 degrees overnight and then maybe creeps up to somewhere around 8. So let's say that the average is perhaps 4 or 5, being generous. So it's actually slightly colder outside on average in this day. And if we have a look at the flow temperature graph, you'll see now that I've actually fixed it. So I've put the device back on the boiler, so it's doing the whole weather compensation thing. Now, if I switch to my Octopus app, this is my gas consumption data for that week, starting the 23rd of Feb 2024. So if you remember, the first day I showed you was the 23rd. This is when the device was turned off, but it was actually slightly warmer outside. You'll see I used almost 50 kilowatt hours of gas on that day. And then the subsequent day, the Saturday, which is when I fixed the device, and it was actually slightly colder outside, I used only 40 kilowatt hours of gas. So in that case, it looks like the device saved about 20% of our gas usage for that day. Now, obviously, it's very difficult to extrapolate this to an overall figure, but even if it's only a 10% saving, that's still a significant amount of CO2 reduction and a significant amount of cost saving. So I really do think that this is worthwhile and is making a difference. Very final thing that I wanted to say was, if anyone is interested in turning this thing into a product that people can slap onto the front of their boilers and have it all just magically work, please get in touch because I think that would be really cool. See you next time.